Okay, yeah, welcome everyone with this second lecture. So I thought maybe it's good to just go over the notes a little bit from yesterday. Just recap what we did, and maybe there are a few people who were not there yesterday, and they can catch up. So we discussed a brief outline of the lectures. Yesterday we mostly discussed instantons and then the required aspects of SUSY QFT. Then this lecture will today deal more with topological twisting of these supersymmetric quantum field theories and their correlation functions. And then the lectures next week will specialize to a few more advanced theories compared to the basic theories, including hypermultiplets and the five-dimensional theory, which capture interesting invariants of the instanton moduli spaces. Last spring I gave lectures in Elmhurst, and if you're interested, you can find lecture notes on my website if you go to the section with recordings and lecture notes. Those lectures are a bit more concise version of the lectures I'm discussing these days online. Okay, so in last lecture we discussed these we reviewed a few basic aspects of Yang-Mills theory and its action. We introduced this complexified coupling constant tau, which is theta over 2 pi plus 4 pi over g squared, and then we discussed that the instanton solutions, or the so-called anti-self-dual solutions, minimize the classical action, and that there is in fact a moduli space of these solutions, which are classified by their instanton number k, which is an integer. This is a rather complicated space, in particular because of this action of the full Gates group of Gates transformations. You've seen that if you evaluate the action on an anti-self-dual solution, the action depends holomorphically on tau. A priori, it's g squared and theta are independent parameters, but on these instant solutions, we get a holomorphic function of tau, and we get in general power series then in terms of this variable q to the k. We looked at this explicit solution for instanton R4, the so-called BPST instanton, which is given in terms of the Pauli matrices. And in this is a solution for instanton number k is equal to 1. And if we look at the energy profile, takes the following form. We get some kind of bump function that goes to 0 energy at infinity, since there the solution becomes pure gates. If we send this row to infinity, this goes to 1 or minus I, it becomes pure gates, and therefore we have vanising energy. And then we get a bump in the middle, and the width is determined by this parameter t. So this is then one of the parameters of these moduli spaces of solutions, together with the position of this bump, and you could then also still rotate the solution, giving you extra parameters. Maybe let me break here also for a second to see if there are any questions or any suggestions to go over material. Again, more detail, happy to do so. Okay, if not, then I'll just continue. We then moved on to introducing the supersymmetric theories, which include fermions and spinors. So we introduced the notion of spinor bundles as the bundles associated to SU2 plus and SU2 minus of the so-called spin group. Spin 4 is the double cover of SO4. And then we discussed that the matter content of these n equals 2 supersymmetric theories organizes itself into multiplets, the vector multiplet and the hypermultiplet, The vector multiplet consists of a scalar field, complex scalar field phi, in the adjoint representation of the Gates group. We have, of course, the Gates potential, this element of the vector multiplet, and then we have these spinor psi I running over 1 and 2. Those are the 1 and 2 of the n=2 supersymmetry, and the spinor index alpha for the two-dimensional spinor bond. And then there's the conjugate fields psi bar I alpha dot. And it's useful, this will come back to in the lecture today, to consider the dimensions of the representations of these various SU2 groups. The first two entries are from the rotation group or spin 4, SU2 plus and SU2 minus. The last entry is then the SU2R symmetry group, which is the symmetry group which rotates the two independent sets of supercharges into each other. So then the phi is just a one-dimensional representations for all these groups. A mu is a vector, so we get 2, 2, 1. And the fermions are, the chiral fermions are 2, 1, 2. And the anti-chiral fermions are in 1, 2. Sorry, this should actually be 2 as well. 1, 2, and 2. Okay. Then we discussed the hypermultiplets, which are multiplets which involve two complex scalar fields, traditionally denoted by Q and Q tilde. This Q is, of course, different from the Q I used for the exponentiated action, but I hope that's clear from the context. The Gates transformations then act from the left on Q and from the right on Q tilde. So they are conjugate, they transform conjugately under the Gates transformations. And they form then these representations under the three SU2 groups, 1, 1, because they are scalar fields. Then this element Q and Q tilde dagger is two-dimensional under the SU2R symmetry group, and the combination minus Q tilde Q dagger is also two-dimensional. Okay, and this also comes together with fermions to get a supersymmetric multiplet. So we have fermions lambda alpha, chi alpha, which are elements of the chiral spin bundle times the appropriate representation of the Gates group in 2, 1, 1, and lambda dagger alpha dot, chi dagger alpha dot in the anti-chiral spin bundle. Okay, we can, in the presence of hypermultiplets, introduce another parameters in the theory. These are the masses of the hypermultiplets, masses mj, where j then runs from 1 to nf. We usually say that we have nf hypermultiplets or nf flavors. F stands for the flavors. And a bit depends on the choice of your masses. You can have different global flavor symmetries. If all the masses are equal, we have SO2 and F. And if we give them all distinct masses, we just have a U1 to the NF, where each U1 rotates. It just acts on a single hypermultiplet. Okay. Is that okay? Are there any questions? Okay, then we discussed a little bit the supersymmetric vacua of this theory, the configurations where the potential vanishes. We have a D-term potential. V of 5 is 1 over G squared trace phi dagger squared, minimized by phi dagger is equal to 0, which can be reached, and solutions to this equation can always be brought to this form where phi is equal to A0, 0 minus A, for A complex number. And then the off-diagonal terms here, they become massive due to the usual mechanism of spontaneous symmetry break. And the same happens for the gates potential. On the diagonal, we get the gates potential for a U1 group, and then off diagonal, we get massive W bosons whose mass is equal to absolute value of 2a, where a is this parameter here in the classical value for phi. Okay, then we introduced this combination, the trace of phi squared, since a gate symmetry can flip the sign of A, and therefore it's not phi itself is not gates invariant. But if we consider this combination the tray of phi squared, we get a gates invariant order parameter on this branch where the gates group is spontaneously broken from SU2 to U1. Classically, this then starts with 2a squared. Quantum mechanically, if you think of this as a correlation function, we get infinitely many, there's a whole series of subleading corrections. Okay, so our main interest in these lectures is, or important interest in these lectures is to consider this Coulomb branch, where the theory is the gate symmetry is broken from SU2 to U1. U1 field theory is much easier to deal with than an SU2 field theory, and we can use this low energy effective field theory to do calculations. Yet this theory is strong enough in a sense to give us exact answers for these topological correlation functions which know about the full SU2 theory. Okay. Now, besides the Coulomb branch, there's also a so-called Higgs branch where the gates group is completely broken. At the Higgs branch, the field phi is equal to 0, and then we get these conditions for the scalars of the hypermultiplet, namely Qj, Q tilde j, and then the traceless part in the with respect to the space of the gates group should equal 0, and also this difference of Qj, Q dagger j minus Qj, Q tilde dagger j, the traceless part should be equal to 0. Okay, any questions? Okay. We've discussed the various BPS states. We have seen the instanton solutions already. Then the W bosons leave invariant half the supersymmetry. Besides, we have also monopole solutions, the so-called 't Hooft-Polyakov monopole, where phi goes to this diagonal form for at infinite distances. And these are also massive states where the mass is given by tau times A, where A is the asymptotic value. And then there is an analog, which are the dions, which are monopoles plus electric charges. So they are very similar solutions. And their mass is equal to tau times A plus 2 times the electric charge N times A. So in the low energy effective field theory, these massive states are all integrated out. They are not dynamical states, but they give rise to non-perturbative corrections to the effective action. Okay, then we discussed some aspects of the RG flow for these theories. In general, the coupling constants become dependent on the energy scale in quantum field theory, and this has the consequence here that our complexified coupling constant tau becomes dependent on the energy E through this logarithm, and this dependence is governed by the beta function in the following way we discussed. Okay, and in this, then going back to the Coulomb branch, the role of the energy is taken by the parameter A. So we get a function tau of A, which is the UV coupling constant tau UV you assign to define the theory, and then we get this logarithm A divided by lambda UV plus further corrections. We can trade these UV parameters for an effective parameter lambda in the following way. Then we don't have to keep track of the UV coupling. Okay. Furthermore, the effective action is completely determined by supersymmetry in terms of the holomorphic prepotential Fa and lambda, and this prepotential then determines this mass of the monopole just by taking the first derivative of F to A, and the coupling constant tau corresponds to the second derivative of F to A. Okay. Any questions so far? See, I'm taking some time to review this, but I think it will come back later in the lecture. So I think it's actually useful to go over it again. Then we discussed the Seiberg-Witten solution. This is the solution that gives us all these corrections, which is able to give it all these corrections. The solution is given in terms of an elliptic curve, and this elliptic curve depends on the parameter u, the order parameter on the Coulomb branch. So we have an explicit algebraic equation which depends on this parameter u. And if we change u, then we change the shape of the elliptic curve. So here at the bottom we have the u plane, and then at different points in the u plane we get a different elliptic curve. And there are two singular points where this elliptic curve pinches, and the physics of this is that at these points, in this spectrum of massive BPS states, there will be a state which becomes massless, either the monopole or one of the dions. And so since we integrated these out, assuming that they are massive states, the effective theory breaks down because the particle becomes massless and therefore should be taken into account in the lower energy effective field theory. Okay, and in this solution, then A and AD are given as period integrals over specific cycles A and B of this elliptic curve. We can make everything explicit if we consider the Seiberg-Witten curve as a double cover of two planes for the x coordinate, and they are distinguished by y is equal to plus or minus the square root of the right hand side. Then we can pick the cycles A and B, which precisely correspond to these parameters. Okay. Any questions so far? Okay, now this brought us to the subject of elliptic curves, elliptic integrals. This subject, modular forms play a big role, as we also see for evaluating the path integrals. So we went briefly over the definitions for modular forms. So these functions are functions of complex analysis from the upper half plane to the complex numbers, and they are required to satisfy this transformation property, namely for an element gamma in SL2Z, which are the 2x2 matrices with integer entries and determinant 1. F should transform back to itself if we replace its argument tau by a tau plus b c tau plus d, up to a prefactor with an exponent known as the weight c tau plus d, and the possible phase epsilon gamma. Epsilon gamma is a phase. Or a root of unity. And we have a few examples. We have the examples of the Jacobi theta series. They actually transform in a so-called congruent subgroup of SL to Z. And we have the example of the dedicant eta function, which transforms under the full SL to Z. Then in terms of these functions, we can express U as a closed expression in terms of tau. So this is a powerful result that we have a full, completely analytic expression for U in terms of the effective coupling tau. On the right-hand side, we have theta 2 to the power 4 plus theta 3 to the power 4 divided by 2 times theta 2 squared times theta 3 squared. You see we have in the numerator and the denominator we have 4. It's degree 4, such that this is the weight is actually equal to 0, and U tau is invariant under the congruence subgroup. And the congruent subgroup is in this case denoted by gamma 04, upper 04, which means that the upper right entry B is equal to 0 modulo 4. Okay. Okay, now we would like to get a one-to-one map between these the coupling constant and U. You see that the coupling constant, because of the logarithm, is actually multi-valued. If tau is equal to log of A over lambda plus terms, so we could replace A by U if you want to write it as function of U over the square root of U, or put U here and then a 4, change the 2 by a 4. The subleading terms will be slightly different because U is also a complicated function of A. But this is multi-valued, and we would like to get a one-to-one function which we can obtain by restricting the domain of U. And this fundamental domain is the following. It is this 6 copies of the keyhole fundamental domain of SL to Z. We have 6 copies, 4 here next to each other at the top, and then there are these 2 copies near the horizontal axis. And these are the 2 cusps. If you go to weak coupling, G to 0 or tau to I infinity, we go here to tau to I infinity, and then we have these 2 other strong coupling singularities where tau goes either to 0 or to 2, where the monopole or the dion becomes massless. Okay. All right. Are there any questions so far in the review? Okay. Sorry, this was a leisurely review, but I think it is useful to recap a little bit. Okay, so we'll continue with the lecture today to formulate this now on a general Four-Manifold. We have a few conditions, and then we want a smooth, compact, and oriented Four-Manifold. Denoted by X. We have a few topological numbers which characterize as X. So basic one is the Euler number. Chi, which is the alternating sum of Betti numbers. It's -1 to the j, bj, j running from 0 to 4 in our case, and and Bj being the dimension of the jth cohomology group. Now the second homology group, H2, naturally takes the form of a lattice. So for alpha and beta in H2, XZ, we have a bilinear form Bx from H2 times H2 to Z, which is given by Bx alpha beta is just the integral over x of alpha wedge beta. We get a 4 form if we wedge these, if we multiply alpha and beta. And if we if these forms are appropriately normalized, then this is in fact an integer. And so we get a B2 dimensional lattice. Let's redenote by L. L is equal to H2, but modulo, if we mod out the torsion, and this actually, one can show that this is a unimodular lattice, which follows from Poincare duality. Okay. Typically, this lattice is indefinite. We have a few positive definite directions and a few negative definite directions. So this is the difference is known as the signature. Sigma is B2 plus minus B2 minus. These are positive and negative definite the dimension of positive and negative definite subspaces, sublattices of L. L times R, so not always aligned with the lattice. And so this is another important quantity for the topological nature of these spaces. Okay. Any questions so far? So we will assume, basically for simplicity, we assume that X is simply connected and therefore B1 is equal to 0, which is equal to B3. And also it's also if it is simply connected, there's no torsion. to get interesting results, then we actually need that B2 plus is odd. Since otherwise the correlation functions vanish for reasons I cannot directly explain at the moment, but we make this requirement. Okay. Any questions? Okay, I would like to discuss a few aspects about smooth four-manifolds. Maybe also, I see there's an interesting talk tomorrow scheduled at the same time about the mathematical aspects of smooth four-manifolds. So let me briefly go over a few basic elements. We say that we have a smooth atlas if all the transition functions are smooth. Yes. Atlas is an atlas for a manifold for which is an atlas for which all transition functions are smooth. Now we have an equivalence relation between smooth atlases. Two atlases are equivalent or smoothly equivalent if their union is smooth. And then we can introduce the notion of a smooth structure. A smooth structure is a collection of smoothly equivalent smooth atlases. A smooth structure is a collection of smoothly equivalent atlases. And if you have two equivalent smooth structures, then these are related by a diffeomorphism. Two equivalent smooth structures are related by a diffeomorphism. Okay, so yeah, it's an interesting subject in mathematics. I believe we will hear more about tomorrow. To classify then four manifolds up to diffeomorphism, or to classify the smooth four manifolds. And I'll discuss a little bit later how this relates to the physics. How this turned out that physics has some has some bearing on this this problem. Okay. I would like to say a little bit about spin structures. We saw already a bit of spin structures in the review. Let me just say that we recall that spin 4, group spin 4 is isomorphic to SU2 plus times SU2 minus. It's a double cover of SU4. That means we can write it as this exact sequence. Spin 4 to SO4 to 1. Now, not all four manifolds do admit a spin structure. There's a topological condition known as the second Stiefel-Whitney class, which has to be 0 in order for X to admit a spin structure. Let W2 of X be the second Stiefel-Whitney class of X. Then X X admits a spin structure if and only if W2X is 0. Is 0 in H2X Z2. These Stiefel-Whitney classes are elements of H2X Z2. And we need to have a trivial Stiefel-Whitney class in order for X to admit a spin structure. So this means only these are the manifolds which are spin, for which we can introduce spinor fields. If W2 of X is not equal to 0, it does not admit spinor fields, and we need to do something special. Okay. Any questions? Okay. So what the special thing we need to do is that we need to go to so-called spin C structures. So for us, just as a spin structure, recall that the spin structure was a principal spin 4 bundle over X, which was compatible with the rotation group with the action of SO4 on the tangent bundle. Similarly, we can have we can introduce a spin C4 group, and that will give us a spin C structure. So the spin C4 is the following group. Where earlier we had these groups SU2 plus, SU2 minus, and now we get two U2 groups. So we have elements U1, little U1, little U2. We require that their determinants are equal. And these elements are both U2 matrices, so more general than the SU2 matrices of spin 4. And we can write the spin C4 then in a similar way to this. That spin 4 is a double cover of SO4. Now we get for spin C4 we have extended SO4 by a U1. So we can write it as 1 to U1 to spin C4 to SO4 to 1. Okay, any questions here? So the problem for some manifolds, if W2 of X is not equal to 0, for it to admit a spin structure is that if you have the different patches, if you try to make a spin-4 bundle over X, then the signs on intersection 3 intersections might not work out. They don't. If you multiply the different the transition functions, they're not multiplying to 1, but they differ by a minus sign. Now, in this larger group spin C4, we can avoid this problem, and there's a result that any Four-Manifold does allow for such a spin C structure. Okay, so let me just specify this, that a spin C structure S is a spin C4 principal bundle compatible with the tangent bundle. And it's a result that any oriented Four-Manifold does admit a spin C structure. It's okay. Okay, and now these two factors, the U2, they give rise to the spin C bundles, which is known by W plus and W minus, in analogy to the spin bundles S plus and S minus we had earlier, in case the manifold is spin. W plus minus are the two parallel spin bundles. Spin C bundles with respect to the two factors of U2. Okay, any questions? Okay, we can consider the determinant line bundle. We required here that the determinant of these matrices U1 and U2 is the same. So we can consider the determinant bundle with respect to either W plus or W minus. Let L be the determinant bundle. curly L is the determinant of W plus minus. And then the Chern class of this bundle actually satisfies the following: the characteristic class of the spin C structure, the characteristic class C of S, which is equal to this first Chern class of this line bundle, satisfies the following: C of S is equal to W2 of X, this Stiefel-Whitney class, and then modulo elements of H2 X of 2Z even elements. So if W2 of X is 0, then we can divide C of S by 2, which means that we can take, in a sense, take the square root of this line bundle, which means that we can reduce the spin C structure to an actual spin structure. If W2X is not equal to 0, then we cannot take the square root of this bundle. It's not well defined. Okay, there's an almost complex four manifold. There's a canonical spin C structure. And I have been, actually, I should comment in a bit more detail here that I made this assumption that B2 plus is odd. Now, if B2 plus is odd, then one can show that the four manifold is almost complex, allows for an almost complex structure. And this means that the tangent bundle of the four manifold is a complex manifold itself, and therefore we can discuss Chern classes of these bundles, which are only introduced for complex manifolds. So I was implicitly assuming here that that we have an almost complex four manifold. Now, this is an almost complex four manifold. There is a canonical spin C structure. Structure where CS is equal to the canonical bundle of the four manifold. And if we choose, so we have this also shows that we have an infinite family of spin C structures. Now here there is a canonical one, and for the canonical one, we have the following identification of these chiral spin C bundles. W plus is identified with even differential forms, 0 forms plus forms with Horst degree 0,2. And the negative chirality bundle is identified with differential forms with degree holomorphic, anti-holomorphic degree of 0,1. And then the Dirac operator takes the form of a double operator. Okay. Okay. Are there any questions at this point? Okay, so the next subject is topological twisting. So maybe since we are this is a natural breaking point to take a little break, and we'll continue in 5 or 10 minutes. Okay, are there any questions about the first bit? Okay. So yeah, these aspects of the spin C structure versus spin structures will play a role later, especially when we discuss topological twisting of hypermultiplets. Now we continue with topological twisting, introduce topological twisting with focus on the vector multiplet. So as we have seen that there these four manifolds in general. Four manifold is not a spin manifold. There's a topological condition that the second Stiefel-Whitney class vanishes for the manifold to be spin. Yet the super Young-Mills theory I introduced had many spinor fields, or the fermionic fields. So topological twisting is a technique which allows us to still formulate supersymmetric Young-Mills on a four manifold. On the four manifold, possibly non-spin. And the second purpose, which is also in the name, is that we can arrive at a family of topological correlation functions. Correlators, which means they are independent of the metric. So in short, what topological there for the theory we are considering, n equals 2 supersymmetric Young-Mills theory, there's one topological twist we can do, the so-called Donaldson-Witten twist. And this is a bit to distinguish it from theories with more supersymmetry, such as n equals 4 Young-Mills, which allow more possible inequivalent twists, like the Waffa-Witten twist and the Langlands or Kapustin-Witten twist. Now the Donaldson-Witten twist, what it does is that we have this SU to R symmetry, the SU to R symmetry of the theory gives us you could say it as a flat SU to R bundle over our manifold a priori. Say for the moment let's restrict to that our manifold is spin. That we can formulate. We don't have any issues with the spinners. Then we can decide to make this SU to R bundle non-trivial, and for example, let it coincide with one of the chiral spin bundles. This is what, in a sense, topologically twisting does. It chooses the SU to R principal bundle isomorphic to the SU2 plus chiral spin bundle, isomorphic to the SU2 plus chiral spin bundle. And I'll assume here that X is a spin. Then we'll see in a couple of minutes how to generalize this. Okay, maybe a bit more formally, we can phrase it as follows: we choose a homomorphism between groups homomorphism phi from spin 4 to our R symmetry group, SU2R. And we'll see later also the flavor group. And then we get a new Lorentz group, in a sense, this gives rise to a new Lorentz group, spin prime 4. Which coincides with 1 times this image of phi acting on spin 4 contained in spin 4 times the SU2R group. Okay. This can all be generalized and extended. There's a recent paper by Greg Moore and collaborators from about a year ago where they discussed this topological twisting in quite some further generality, but just here as a first introduction. Okay, so we get this new Lorentz group. Now we require for this group to be to define a topological twist. To get these topological correlators, we require that the following, namely that if the induced representation on the supersymmetry generators should involve a scalar supercharge. So let rho of Q be the spin 4 times SU2R representation of Q I alpha. Actually, I want here spin prime 4 representation of Qi alpha. Then rho of Q must contain a singlet Q. Must contain a singlet under spin prime for Q. Okay, so this map phi, you can specify this here now. It acts from SU2 minus times SU2 plus to SU2R, and the map is simply 0 on the SU2 minus part, and it is the identity on the SU2 plus part. So as a result, the field content transforms under the twisted fields transform under SU2 minus times SU2 plus prime with SU2 plus prime, the diagonal subgroup of SU2 plus times SU2R. The diagonal subgroup of SU2 plus times SU2R. Okay, are there any questions so far? Okay, so let us take a look how this what we get for the different fields. We had our gauge potential A mu. We saw earlier in this lecture that the representation corresponds to 2 to 1 in the untwisted field. Then we topologically twist, and we get the representation 2, 2 under SU2 minus times SU2 plus prime. Let me just indicate what we have here. These are the dimension for SU2 plus. Here we get the dimension for SU2 minus. And here we have the dimension for SU2R. This is the dimension for SU2 minus, SU2 plus. As I think I want to flip this around. SU2 minus, SU2 plus, SU2R, SU2 minus, and SU2R, sorry, SU2 plus prime. Okay, and so the representation here is the tensor representation of SU2 plus and SU2R in the original field content. So in this case of the gauge potential, we get 2 times 1 is 2. Then for the scalar field, phi, and we have phi bar, we can add both. We get we had just 1, 1, 1 goes to 1, 1, 1. And for the fermions psi I alpha, psi bar I alpha dot, we had this is equal to 1, 2, 2 plus 2, 1, 2. So now we see we get the tensor product of 2 and 2. 2 times 2 gives us splits into irreducible representations 3 plus 1. So we get here 1, 1 plus, so I want to split this a little further, get 1, 1 plus 1, 3 plus 2, 2. Okay. And so these representations, which are, we can all relate, in fact, to differential forms. So this this first one here is, of course, a scalar, a 0 form. Representation 1, 3 is a self-dual 2 form. And 2, 2 is a vector. Okay. Usually we denote these ones, the scalar by eta, the self-dual 2 form by chi mu nu, and the vector by psi mu. But the main thing is that all these are all differential forms. H2 plus. This is, or it's not in the cohomology, it's a differential form. Omega 2 plus, omega 0, and omega 1. And that these are can be formulated on any four-manifold. So here on the left-hand side, we have these spinorial fields which only exist on a spin manifold. But now here on the right-hand side, after the topological twist, the field content organizes itself in multiplets, which can be formulated on a non-spin formula input. On spin and spin formula input. Okay. All right. Any questions here? Yeah. Okay. So similarly, this field content of these fermions in the vector multiplet is actually the same as the representations of the supersymmetry generators. So if we consider these Qi alpha and supersymmetry generators Qi alpha dot, these are also changed to a representation 1, 1 plus 1, 3 plus 2, 2. And for us, the main one is this singlet 1, 1, which is a scalar supercharge. Which we typically denote by just Q. And because it's a scalar supercharge, it's also called a BRST symmetry, very similar to the BRST symmetry of the Fadeev-Popov theory. For those familiar with that. Okay, any questions? Okay, and since Q is anti, there's a fermionic symmetry. Q anti-commutes. So we arrive at Q squared equals to 0. Okay, any questions? Okay, and so now if you have an action which squares to 0, we can consider the cohomology, and indeed the observables of this theory, topologically twisted theory, can be grouped into three sets. Three classes of observables. In the topologically twisted theory. The first one are observables O such that Q annihilates Q does not annihilate the observable. The second class of observables are so-called Q exact observables. Namely observables O, which can be written as the Q of another observable W for some W. And then finally we have the set in the cohomology. These are observables O which are annihilated by Q. So we say that they are in the kernel of Q, but they cannot be written as an element of the second family. So they are in the kernel of Q modulo the image of Q. Or in other words, Q acting on O is equal to 0. But if O was of this form here, then it will be trivially 0 because of Q squared equal to 0. So we require that it is not of that form. That O is not Q exact. Okay. Any questions? Okay, so then one can show the following, that Q exact observables vanish formally. Q exact observables vanish at least formally. Very similar to Q exact observables in Yang-Mills theory. If you quantize it using the Fadeev-Popov method, that these decouple from correlation function. So just to briefly recap the argument, we start with an observable which is Q exact in the correlation function. We can write this as a path integral over the set of all fields X. Maybe it's not such a good notation. X is also the four-manifold, so let me call it phi. Q O e to the minus S phi. And then assuming that the measure is invariant under Q and the action is invariant under Q, we realize that this is equal to 0. Now the Lagrangian takes the following form of the topologically twisted theory. We get a topological term, which is actually precisely the instanton number 1 over instanton density I over 8 pi tau times the trace of FHF. And then there are other terms where the dependence is on the scalar field, the fermions. And this is actually Q exact. So we can write it in this way for inappropriate W. Okay. We can always shift W by something which is itself Q exact, because Q acting on W is vanishes. And now we see that since this term is topological, does not involve the metric. All the metric dependence of the Lagrangian is in the Q exact bit. So the metric dependence of L of the Lagrangian is in the Q exact part. It's in the Q exact part. Okay. It's again a bit similar to the QFT case, where the dependence on the gates on the choice of gates is in the Q exact part of the BRST symmetry. And as a result, we can show that then Q closed observables, I should have Q closed means annihilated by Q. Observables are independent of the metric. Since if we take a variation with respect to the metric G of a Q closed observable, so we need a little more detail here, but then these the action of delta G of O vanishes, and we get the path integral d phi of O times delta G of the integral over X of Q W e to the minus S of phi. But now this, we have inserted the Q exact, pretty much, we have inserted the Q exact term, and therefore this is equal to 0. Because now if we act with Q to the left, it will be independent of O was annihilated by Q, and also to the right, e to the S phi was also independent of, was also annihilated by Q. So we arrive at the following, that to introduce the theory, we need to introduce a smooth structure. This is what we need to introduce derivatives in the action, write down the equations of motion. So our theory, our correlation functions, these topological correlation functions do depend on the smooth structure. On the other hand, we also arrive at the result that these correlation functions are independent of the metric, and so in this way, physics is able to distinguish among smooth structures. So it's correlation functions O do not depend on the metric, but do depend on the smooth structure. Since that's what you need to introduce these differential equations, giving the equations of motion. So we see that physics is, at least in principle, there's the potential that physics is able to distinguish amongst structures. Physics potentially distinguish among structures. And that's in the sense what we will arrive at, that the mathematicians developed the notion of, or in particular, Simon Donaldson developed the notion of Donaldson invariants, which can distinguish among smooth structures, but are independent of the metric, given that some topological condition B2 plus is not equal to 1. And then with the topological twisting developed by Witten, one can understand that these Donaldson invariants are correlation functions of these topologically twisted theories, and this is then further developed with the Cybers-Witten invariants, which in a sense capture the Donaldson invariants. So what are examples of Q-closed observables? First example is pretty much the same as the order parameter of the Coulomb branch trace phi squared. This is what we call a point observable because it just depends on a point x on the manifold. And the second one is what we call a surface observable. Actually, I think this is now not a very good notation. Let me call it P for point. The second one is a surface observable, I of x, where x is now a 2-cycle in x. Little x is 2-cycle in capital X. And with the appropriate normalization, it looks as follows: 1 over 4 pi squared integral over this 2-cycle x, and then the trace over psi wedge psi minus 1 divided by the square root of 2 phi wedge f. Okay. And yeah, and one can continue. There is also observable for the full Four-Manifold. Actually, there are also ones for 1 cycles and 3 cycles, and these observables are related by the so-called descent formalism. Any questions? Okay, and so actually, let me call this one here. I will denote it by U. It's a little bit abusive notation since U here is not a correlation. It's not a correlation function. It's just this operator. We'll see later actually that it's not as bad as it looks, but okay, here I use U as for this operator. Now we can consider correlation functions of the form U to the R I X to the S. Since it is topological, actually the position it will be independent of the precise position of these operators, because you can varying the metric to change that. And now these topologically twisted theories, such correlation functions, are precisely equal to the Donaldson invariants dr, s. This is a Donaldson invariant. This is an element. It's a rational number. A rational number. And these, you have to take care of the dimensions. So these have dimension the scale squared, and this has the dimension of the the dimension of just one factor of the scale. So this goes as lambda to the 2r plus s. And this Donaldson invariant is precisely an integral over the moduli space of instantons. There's a moduli space of instantons. And such that the dimension of mk is equal to 4r plus 2s. And what we are integrating is our certain differential forms, which I will denote as omega u to the power r, which is a 4 form, and omega omega I to the power s. And this is an element of the 4-dimensional cohomology of mk, and this is an element of the 2-dimensional cohomology of mk. Okay, so in general, we have a Donaldson, so-called Donaldson map. I'm expanding a little bit here on the Donaldson theory. We have a Donaldson map which associates to cohomology classes of homology classes of X. Sorry, homology. You take a homology class of X, and it maps it to cohomology of the moduli space of instantons. In a dual fashion, where this is 4 minus star. So this way we see that we have it maps a point. If we have a point here, or where star is equal to 0, here on the right hand side we get a 4 form on mk. So that's why omega u or omega is associated to the point, and it associates to a 2 cycle on h. This is this 2 cycle x. It associates then a 4 minus 2 is 2 form on mk. And in order to get a non-vanishing result, we need to just span the full dimension of the moduli space, and that's how we get this combination of 4r plus 2s. This is, I should say, the yeah, okay. Okay, we can determine, starting from the moduli space of instantons, we can determine what is this, what's the dimension of the moduli space of instantons, and this corresponds to 8k minus 3 times the combination chi plus sigma divided by okay, so any questions at this point? So this last bit is a bit of an overview, of these Donaldson invariants, just the basics, how they are, really the essentials of how they are developed in mathematics. There are intersection numbers of these classes on the moduli space of instantons, and one can show that they are independent of the metric, but do depend, are able to distinguish among smooth structures of 4 manifolds. And then in this this relation, this is how they come out from the physical perspective. If we consider topologically twisted field theory, the theory without the hypermultiplets, in fact, just a basic vector multiplet, then these type of correlation functions evaluate or capture the Donaldson invariants. Okay, so this is still a bit, maybe a bit qualitative. We can make this actually very, really very precise. So that's what we will develop in what follows, to look into this in more detail. So we consider the path integral of this topologically twisted theory, or this correlation function. So in general, this path integral will receive contributions from these two supersymmetric vectora. We have seen the Coulomb brands and the Higgs brands. Or in this perspective, we get a path integral on the Coulomb brands. Plus a delta function support. At singular points, these singular points of the Coulomb brands, where the some of the massive states became massless. Delta function support at singular points. Where generically massive, where their a generically massive state becomes massless. And so this, more in a formula, takes the following form. Sorry for the abuse of notation. Now I use phi for this contribution from the Coulomb brands, not for the set of fields. This is the contribution from the Coulomb brands plus the delta, the contribution from the singularities is denoted by the correlation function with subscript SW for Seiberg-Witten contribution. This is the Seiberg-Witten contribution. If you want, you can also think of it as the Higgs brands in the topologically twisted theory. I will comment on that a bit more later. Okay, so now the interesting, this contribution from the Coulomb brands will be of the main interest for us in the coming lectures. An important result is that it is actually only non-vanishing for a special class of four manifolds. But as I will discuss, it is still a powerful tool for general manifolds. So phi O is only non-vanishing for manifolds with B2 plus smaller or equal 1. Now also we were restricting to manifolds with B2 plus is odd, so this will leave for us only B2 plus is 1. And moreover, for B2 plus is 1. Reduces the full path integral, the infinite dimensional path integral, reduces to a finite dimensional integral over zero modes. Finite dimensional integral over zero modes. Okay, and so maybe just to sketch this, we had these functions A, which appeared in phi, but this continues to hold for other of the functions. We have a function A as function of the coordinate Z. We have the constant mode, which is independent of Z, plus a non-zero mode, which I denote by A prime. This is the zero mode, independent of Z, and this is the non-zero mode. Then you can make an argument based on topological invariance. Plus rescaling the metric. G to T squared, G. And T to infinity. We'll show that this is the case. Then you can show that the non-zero modes are actually not contributing. Okay, this is nicely described and many more details in a paper by Moore and Witten on the U-plane integral from 97. Okay, so then in the next lecture, I'm planning to further develop this U-plane integral and explain how we explicitly can derive or confirm that correlation functions reproduce these Donaldson invariants and other types of invariants of moduli spaces for other theories. Thank you again for your attention. I'm happy to take any questions.